Towering telecommunications masts rely on extreme static tension to stay upright. To resist heavy winds, these structures are tethered by steel guy wires that must be pulled tight enough to anchor them to the ground. This same requirement for tension exists inside steel-framed skyscrapers. Cross-bracing in the walls ensures the building remains rigid enough to transfer wind and seismic loads into the foundation. Suspension bridges operate similarly, distributing thousands of pounds of force across a network of cables to support the weight of the road deck. Aviation also relies on this force. Pilots rely on internal steel control cables that must remain taut to connect the cockpit controls to the aircraft's rudders. In these systems, static tension is the force preventing the structure from failing under external loads or its own weight. But establishing that tension presents a specific mechanical hurdle. When you try to pull a cable tight using a standard nut and bolt, the cable itself rotates as you tighten it. This rotation creates torsional stress. Instead of pulling tight, the steel cables bind, fray, and snap under the twisting force. Engineers need a way to apply thousands of pounds of pulling force to bring two ends of a cable together without any rotation at all. The solution is the turnbuckle, a mechanical coupling device that isolates rotation from tension. A turnbuckle consists of three components: a central barrel and two threaded end fittings. One end uses a right-hand thread. Turned clockwise, it moves inward. The opposite uses a reverse, left-hand thread. Because they oppose, rotating the body pulls both fittings inward simultaneously. Rotating the body in the opposite direction pushes the fittings outward, allowing a user to relieve tension just as easily. Because the body rotates independently of the end fittings, the attached cables move linearly toward each other but never twist, solving the torsional paradox. Its strength comes from a fundamental physics principle, the inclined plane. Unrolling the screw thread reveals a long, continuous ramp. This acts as a force multiplier, translating a small amount of rotational torque into a massive axial pulling force. This mechanical advantage allows a single worker with a standard wrench to generate thousands of pounds of tension. The same threads allow for minute, controlled adjustments, letting workers tune a cable's tension or its length with extreme precision. The turnbuckle functions as a tool that bridges the gap between limited human effort and the massive forces required to stabilize industrial structures. Despite its strength, the turnbuckle has specific vulnerabilities, particularly in environments subject to high vibration, like heavy machinery or aircraft. Threaded components are susceptible to vibration loosening. Under dynamic loads, the barrel can slowly back off, leading to a loss of tension. To prevent this, technicians use lock nuts, cotter pens, or safety wire to physically lock the threads in place. These devices also face environmental limits. Exposed threads can rust or seize over time, and the internal threads create a strict limit on how much a cable can be adjusted before it must be re-terminated. In any high-tension system, the threads become a point of stress concentration. If the system is overloaded, this is a likely point of structural failure. While vital for heavy infrastructure, the turnbuckle is also found in everyday setting. It is used in sports equipment, specifically to maintain the precise tension of boxing ring ropes. The design remains unchanged because it is efficient. It requires no electricity, requires no complex hydraulics, and has no internal gears. By mirroring two inclined planes, the turnbuckle provides a reliable way to exert thousands of pounds of force without rotating the cables it holds. It remains a standard mechanical solution for maintaining the structural integrity of the modern world.
That is it for today's breakdown. Next time, we are going to dive deep into another critical mechanical component and pull apart the exact engineering algorithms behind how it works.